Okay, so the next speaker is Lei Mao from Horizon. And he will be talking about IOMMU solutions for seL4.
My topic is IOMMU solution for seL4. And I'm Lei from Horizon Robotics. And before starting, I want to first apologize for my poor English. So be patient. Our company is making SOS chips for vehicle and robot. And about 2 years ago, we starting try to explore using seL4 as a base OS for our SOC platform application. So we meet some problem. One is SMMU. First, introduce some background of SMMU. We need to use some virtualization functionality. If we look inside to SoC, typically there are two kind of IPs. One is CPU, named PE in the figure, and another one is preferred device. Normally, CPU software is widely protected in current software, but the device, most devices have a DMA engine, and previously it is not protected well enough, and DMA device normally will can overwriting any addressable memory on the whole system, and this may lead to some security or safety problem. And IOMMU, similar like MMU for CPU, it provides a virtual address space to this DMA-capable device. It can solving address issue, and also can set up some transparent scale operators to prevent the violation of the isolation model. The driving force here is virtualization address at this point. And the widely used IOMMU here in our case is SMMU. The virtualization schema used in current commercial hypervisor normally stage 2 only, or one level stage. Someone is stage 1, someone is stage 2. So in seL4 software ecosystem, normally in user space, there are two kind of software. One is native seL4 components, small components. Another is bigger seL4 VM monitor and guest OS. Both of them can through the unified kernel interface, which systematically manage all SMMU hardware abstracts, and so through this function, both of them can get I/O virtual address space for the device. Typically for VMM software, the device virtual address will be share same view with CPU's SMMU Stage-2 address, and for small device components, the VSpace can be different, because in seL4 is user space view. There are many different kind of components, different like monolithic kernel. So the address can be different across the components. So currently exist stage 2 only schema is simple enough and can be used for some evaluation. currently, stage 2 core work like this. It will give some capability about the stream ID, which is a device use SMU present itself. And there is a context descriptor capability, which conveys the translation item, and finally it will bind with VSpace, and these can use together to finish the virtual space management. And so currently in the ST entry, the quantity descriptor is not used. And this normally is SMMU version 2. And in version 3, there is some change. I will talk later. So although IOMMU Stage-2 only scammer is simple and enough to use for most cases, but in order to address the problem of physical memory fragment and to avoid the bounce buffer, we think a preferred approach is to enable parallelized virtualization, because currently still exists some legacy DMA IPs, device, which can only access 24 or 32-bit address. So with the help, the DMA can combine small fragment together to make a larger frame. For example, if a digital camera have a very large pixel, it need a continuous memory. So this is a similar scenario. Just explain in the whole picture. So for this, first in mind, we support guest OS with SMU is a virtual methodology, and what we need to do is interpreting the requests from the virtual front end, pass all its parameter into SL4 kernel system core. The backend here is very lightweight, just similar like bypass. So as a result, we did the following things to support SMU version 3 in SL4. First, we porting and modify the SMU version 3 driver in the SL4 kernel. Here also has some choice because version 3 removed the register view. Version 2 is based on register. Version 3, all the stream ID, the content descriptor, all other things are based on memory, and this needs some dynamic memory allocation. And if we stage 2 only, ARM remove the content descriptor concept. So we first thought this is a big change. If we dynamic memory and no content descriptor capability, we think we'd better put it in user space. Do not change kernel, but finally we will still keep in kernel. Because if we move to user space, some maintain operation cannot be achieved because of the VSpace, some on-map operation need to operate automatically. If we keep in user space, maybe there's some interaction between user space and the kernel space. And to support version 3, we also made some change because currently in mainline SL4, it is support version 2 SMU. So we modify Haskell script and the root server to generate the seed and the CB objects. And we updated the template to configure the device specific capability and components for the virtual machines. As you see, mainly we add the VM name and SMID. It means SMMU IP instance. Because in our SOCs, there may be multiple SMU support. And SID is the stream context ID for a device using this SMU controller. So finally, we change kernel. This may not make a verification engineer unhappy. So, but in fact, it just changed a little. And as I know, I'm ARC64. The SMU file is not covered by verification, so it can be do more discussion. Here, I just want to mention one thing. Is here we finally decided to support the stage 1 content descriptor bind. That means we want to support stage 1 also in version 3. And upper interface change for function is mainly added for version 3. In version 3, it has some different error, event queue, and something like this. So just its functionality. And the struct is the change is mainly for parameter for them. One problem why we finally choose stage 1 is illustrated here. In SL4, it has capability to manage the frame and virtual space. So if we already distribute the region into one huge or several large frames, if we want to use it as a known memory for the I/O device, it will be a problem. So to resolve this problem, maybe have a choice. For example, create a new type, a new object and cap for I/O space. But it was very heavy and complex. So we think it is not worth. So we do not use this way. And second one is for support different guest OS. Do we need a complex virtio-smmu backend? The answer also no. We just want to make it simple and universal way to make ARC64, which can help. Okay, so finally we support the schema of stage 1 plus stage 2. And the stage 1 will construct I/O page tables, which was realized and managed within VM. And VM monitor itself don't need to own and configure stage 1 context descriptor. It just give a pointer to the memory, keep the context descriptor. Is okay. So the IOMMU API here is extended just to convey the information of guest stage 1 configuration information, and the hook is implemented in the guest. Here, this page show stage 1. We need pass some information through seL4, maybe some TDBR, some ACID and MAR information. And there are also some hypervisor core to update when there is some change in the mapping entry. And also there are some TLB maintenance also through the same way. And if we to support stage 1 plus stage 2, in fact, it is one core. Just core, the API we added, first bind stage 1 connected descriptor pointed to the pointer area, and then call stage 2 or original stage 2 system core to setting up the information. Then everything can work. And the additional benefit of stage 2, currently after stage 1 plus stage 2, then stage 2 can also provide the isolation of multiple VMs. Finally, for native components and VM components, we can support all modes or schema original supported by SMMU version 3. Its mode has some, each stage, stage 1 or stage 2, each stage has some mode for bypass. Bypass means to do nothing, or abort some access operation, or make it work. So for native on stage only to transfer translation has three type. So for VM maybe has more. But in fact, we mainly suggest to use stage 1 plus stage 2. So as a summary, with all this previous mentioned, SMU stage 1 plus stage 2 can be supported without add a new kernel object and capability. And this design can be applied to use all models which SMU version 3 supported. And with S1 supported, Linux native SMU driver can keep original operational logic. No need to use heavy QEMU and virtio-smmu backend. The future plan. Currently, we change it, CamKit template and configure manually. Later, we need a pass device tree of guest OS to generate SMU device node and related caps to the build files. And we also need to do more verification in real SLC platform. Currently, we develop and verify SMU version 3 in FAP platform. And we plan to test a real vehicle application in our next Gen SLC about SMU version 3. And some PCIe device have a very strange SMU ID, which need some deep test also. That's all. Thank you.
Okay, we have time for one quick question, which is Ken.
I might waste the question. What hardware platforms support What hardware platforms are available to buy that have the SMMUv3?
Currently, our company chip in production do not support version 3. Well, when the next chip support, in development environment, we use FAP from ARM. It supports for SMU version 3. And the QEMU do not support the stage 2 translation. So we didn't buy SoC in the market, so we use FAP for verification currently. Yeah.
Right.
Yeah.
Does anyone know of any boards? There's like
there's one from TI that's automotive focused that has like a dual core Cortex A72. Some of the newer NVIDIA ones.
Yeah. So is there any reason we have to put the IOMMU driver inside the kernel?
Yeah, in fact, SMU is a very fundamental IP from ARM. It should be inside the kernel. And previously, we want to move out just because of some dynamic memory allocation and its concept of CB remove. Yeah.
I guess the different way to ask this question is, can the IOMMU be controlled from user level?
Yeah, if IMU controlling user level, so currently IMU, if you map, you still need a object and a cap, right? Currently we only have VSpace. We don't have IO VSpace, right? So, so typically for VM case, the MMU and the SMU will share the stage 2 page entry. The reason is why we introduced stage 1, because DMA can request many small pages, but a small page he requests maybe already allocated by other software. That make a problem I mentioned here. So it cannot be achieved. So stage 1 need introduced, and with that, the stage 1 context descriptor capability is connected to VSpace. So when device do some unmap, it will delete, for example, delete seed cap and object. So related TLB invalidated operation need performed. So if that kind of project and the management is in user space, then kernel, for example, if one software use same address requests this operation, kernel may need notify user space components to do these things. There is a loop in this case.
All right. It looks like there might be more questions, but we should take those offline. And yeah, let's thank the speaker again.